Okay, so we're going to look at molecular compounds and how molecular compounds are different than ionic compounds that we talked about earlier on. Okay, but anyways, a molecular compound, okay, for example, would be something like carbon dioxide or carbon monoxide or nitrous oxide. Those are all molecular compounds. Okay, and they're formed by something called a covalent bond. Okay, which is different than a ionic bond, and we'll talk about that in a second. Okay, but a covalent bond is formed by two atoms sharing electrons. Okay, it's not one atom giving another atom an electron and the other atom taking that electron, and then they become positive and negative and they're attracted. Okay, it's two atoms where they're like, I want this electron, no, I want this electron, no, I want this electron, and they both just kind of tug a war at each other with this electron, so that this electron, is never really going to one or the other one. It goes to one, it goes to the other one. It's kind of a tug of war, or a sharing of electron um, between two atoms. For example, the diatomic molecule of hydrogen, okay, a hydrogen molecule, not a hydrogen atom, a hydrogen molecule, which is two hydrogen atoms bound together, they share an electron. Okay, they each have their own electron down here. You can see that. And what happens is they come together and they fight over this one electron. Remember, the atoms are all trying to become noble gases. They all want to become stable. Okay, they all want to look like a noble gas. Well, hydrogen, in its valence shell, sorry, has only one electron. Okay, well, the valence shell of at the first energy level, the first orbital, should always have two electrons. So in order to look like to look like helium, what hydrogen has to do is gain another electron. Okay, and by creating a hydrogen molecule, it fulfills that two electron orbital, or that two electron in the first orbital, that first valence configuration, by sharing an electron with another hydrogen molecule. Okay, so just remember that they're all trying to look like noble gases, and to do that, they can do that either through ionic compounds, or they can do that through sharing of electrons. Okay, a neutral particle again is composed of atoms joined by covalent bonds. Okay, and this is called a molecule. Okay, um, each atom acquires a full valence shell, just like I said, right? Chlorine, for example, okay, Cl2, not chlorine the atom, Cl2 the molecule, chlorine molecule, okay, is a sharing of electrons. Okay, it's the sharing of one electron for each chlorine to fulfill that valence shell. Just like I demonstrated in the hydrogen, okay, chlorine has one electron that it needs to gain. Okay, so it has this one electron that it needs to gain. So what it does is, instead of one chlorine taking that electron and now we have another chlorine that's missing two electrons, what happens is they share one electron. Okay, and the electron goes back and forth, and one chlorine's like, I want this electron. The other chlorine's like, no, I want this electron. And it's just tug of war between these two chlorine molecules. Okay, in order to fulfill that valence shell. It's never ending, really. It's a continuous tug of war between these two molecules to share this one electron. Okay, so they share this, I guess, this pair of electrons to equal a covalent bond. Okay, each atom needs one electron. Neither wants to give up an electron because the electrons are so attracted to the nucleus. Okay, that they say, you know what? Let's split the difference. Let's share let's share this one electron, and now we're both happy, and now we both look like a noble gas, and we're looking good. Okay, and now we're stable. Okay, whereas ionic compounds are not considered molecules, okay, because there are no bonds created, so there's no sharing of electrons, there's no tug of war. It's simply one ion attracted to another ion because of the electrical uh, opposite charges, okay? So there's simply the attraction between oppositely charged particles. You have sodium, which is attracted to positively charged sodium, which is attracted to a negatively charged chlorine, and they come together to create sodium chloride, NaCl. Okay, so there's no actual sharing of electrons there. Sodium just donates its electron. So this electron comes here, and now sodium can be considered +1, and chlorine can be considered -1, and they come together with full valence electron, full valence shells, full valence electron configurations, and they're attracted to each other because one is now positive and one is now negative. Okay. Substances composed of molecules are molecular compounds or elements. Okay, so they're all composed of substances that are composed of these molecules are molecular compounds. Okay, these are usually composed of atoms of two or more non-metals. So with ionic compounds, we had a metal, sodium, which would be the metal in this situation, bound or attracted to a non-metal ion, such as chlorine. Whereas covalent bonds or molecules um, are two non-metal atoms that share electrons. Okay, two or more non-metal atoms. Okay, so you're going to be looking at the non-metal atoms on the right side of the periodic table. Okay, so for example here we were looking at lithium, sodium. Okay, as metals, and then you were looking at fluorine, chlorine, oxygen, sulfur, nitrogen, phosphorus as non-metals. Okay, and usually covalent bonds happen between non-metal atoms or non-metal elements. Because the formula of a molecular compound represents the actual number of each atom, they're never reduced to its lowest terms. So compounds or molecular compounds are never ever reduced to their lowest form. Ionic compounds, remember I said before that ionic compounds, we need to reduce them to their lowest form because they represent a ratio, where our molecular compounds, they actually do not. Okay, if you reduce molecular compounds, you can form a completely different chemical, a different structure that has different properties. Okay, that might be poisonous, that might not be poisonous, things like that. Okay, so if we look at P4O10, okay, so 4 phosphorus and 10 oxygen, it's a lot different than P2O5. Okay, and you can tell that by its structure. Okay, its structure, it will have a different purpose. Okay, the formula of an ionic compound, like I said, is always reduced because the formula simply refers to the ratio of cations to anions, not the actual number of atoms. Okay, where ionic compounds, um, any ionic compound crystal lattice is composed of many repeating subunits of that specific combination of atoms. Okay, so magnesium oxide. You have one magnesium, one oxide, and that is just repeated a million times or a billion times to form magnesium oxide. Whereas, whereas a molecular compound, you cannot do that. You do not put it into its lowest terms. It is what it is. Okay, P4O10 is a lot different than, again, P2O5, even though they have it has 4 has been reduced to 2 and 10 has been reduced to 5 by dividing both by 2. Okay, a diatomic molecule, okay, is composed of 2 identical atoms. The 7 diatomic molecules are hydrogen, H2, oxygen, O2, nitrogen, N2, fluorine, F2, chlorine, Cl2, bromine, and then iodine. Okay, and these are, again, the 2 identical atoms that are sharing electrons in order to fulfill their valence shell requirements or their valence shell needs. Okay, so the problem is with molecular compounds is that they're very hard to predict the chemical formula of molecular compounds. It's really difficult. We can draw electron dot diagrams to show atoms and how they're arranged, but again, it is difficult to predict the chemical formula of these molecular compounds. Again, diatomic. I just want to stress this again, but diatomic molecules are 2 identical atoms. Okay, 2 hydrogen, 2 oxygen, 2 nitrogen. Okay, 2 identical atoms. Um, So back to predicting chemical formula. Sorry about that. Compound is difficult. We can draw the electron dot diagrams to show the atoms are how atoms are arranged. For example, the electron dot diagram for water. Okay, you have H2O. So you know that there's two hydrogen for one oxygen. Okay, oxygen is located in, if we take a look at our periodic table, oxygen is located in 1716, so we know that its outer valence electron shell will have six six electrons, right? Because this would be 8, this would be 7, this would be 6. Okay, so it would have 6 valence electrons. Okay, so it needs 2 in order to look like neon. All right, so where does it get 2? Well, it gets 2 from the other nonmetal of hydrogen. Okay, well, hydrogen only has 1 electron. Okay, so it only fulfills one of those electron needs. So you need 2 hydrogen now in order to share electrons with oxygen in order for oxygen to have that full valence electron shell. Okay, so you have your hydrogen with its electrons, you have your oxygen with its electrons, and again, the affinity for or the attraction of electrons in non-metals is extremely strong, right? The non-metals want to take all the electrons. They're pretty greedy that way, okay? But they don't want to give up electrons. So why would they give up electrons? They're going to share that electron, right? That's the real difference is they're both non-metals. So non-metals again do not want to give up those electrons. So what happens is hydrogen then forms a covalent bond with oxygen. Two hydrogens form a covalent bond with oxygen, and that covalent bond can be represented as a line right here. Okay,